Okay, good morning to all.
Good morning, sir.
Yeah. Okay, are you able to see this PowerPoint?
Yes, sir.
Okay, thanks. Okay, so we were discussing about the Vsat networks or Vsat systems. So these are very small aperture terminals. So the main aim is to remove the middlemen and directly provide the end user with the reception capability for voice, data, and multimedia services. Like instead of having a distribution hierarchy at the receiving end, so directly the end user will be provided with the option to directly receive the signals from the satellite as per the need. So based on that motivation, this VSAT networks were started. And mainly when we come across the satellite data communications or data services, we can go for broadcast based services or point to point and point to multi point. And sometimes we have unidirectional or sometimes we have bidirectional data transfer. So whenever we go for the broadcast kind of situation, we prefer the unidirectional communication. So it's like a FM radio. So you can only listen to that radio. You cannot reply back anything, right? So that is broadcast, FM broadcasting. So it's mainly predominantly unidirectional. So if you want to talk back to the RJ or something, you have to call them or you have to message them or you have to email them. So directly over the radio, you cannot talk with them. Okay, so that is one example. So based on that motivation, we have seen that in the VSAT networks, a large number of terminals which are dispersed throughout a large area can be connected to a central hub using a geostationary satellite as a medium. So what are the capabilities of the hub and what are the capabilities of a VSAT? So main aim is to uh, reduce the burden at the receiver. Like the receiver can be made portable, flexible, low cost, and low performance, and all the burden has to be shifted towards the transmitter. So that was the main aim. And in that we have seen one typical example is that this VSAT can be used as a alternative for terrestrial mobile communication or telephony networks. Instead of having a terrestrial connection between the tower to the infrastructure, we can have a satellite link. So at the WLL terminal, we can integrate this data to a VSAT terminal, which has a uplink capability also. So from there it goes to satellite, and from the satellite it can go to the main switching center of this telecom network. So otherwise, what we have to do is we have to use microwave or optical fiber technology between this to this. So microwave is that you can see the towers. On the towers, you have this circular plates. So those are the microwave antennas. So using that, you can establish tower to tower link, or you can establish optical fiber. Or this third option is when not much user density is there, you can take the help of satellite and it will send your signals to the main exchange. So this is one implementation of the VSAT. Otherwise, the general implementation is like this. You can either use this hub to connect with these many remote receive only terminals, which is in the unidirectional case, or in the bidirectional case, these terminals will also have a capability to reply back. They also have the outbound or inbound capability also. Okay. Then accordingly, this was just an example. When will this WLL or VSAT be useful? So if you have user density between this 10 to 100 users per kilometer square, then VSAT is a good implementation based on the cost and based on the revenue model. Okay, so all that we don't want. Then what are the VSAT implementations? So three types of implementations are there in VSAT. One is one-way implementation. So this is mainly used for the broadcasting purposes. And there what happens is from the hub, the signal comes to the geostationary satellite and then it is broadcasted to a given coverage area. And due to the introduction of digital services, because of sophisticated software in the user equipment, we can also have a narrowcasting group where a finite group of users have some subscription. So if they have some subscription or they have some special services which is decided by their software package, so they can be given more privileges or they can be given more programs or more facilities. So that is called as a narrowcasting group within a broadcasting area. So these fellows would have paid some money and got some more services. Okay, like advanced encryption or more bandwidth or something like that. Uh, so then the second type of implementation is split or two-way implementation. That is also called a split IP implementation. So in this, what happens is we it's two-way only, but there is no return channel. Okay, so split IP is also two-way, but there is no return channel. So suppose if you get some internet facility, then there is no way that you can talk back to your server. Okay, so only the unidirectional, some streaming kind of thing is possible if you have the split IP implementation. Then, okay, and purely two-way is also possible where there is a forward channel as well as a reverse channel. Okay, so in the split IP, only a broadcast satellite service is used to provide the coverage. And if you want a return channel, so these are only one directional. If you want a return channel, you have to go back to your mobile phone and or telephone and use it for connecting with that people. That is the split IP implementation. And third one is the two-way implementation. So two-way implementation lends itself to either star networks or mesh networks. So in the star network, what happens is uh, the hub acts as a central place. Like this is the example for star. Okay, so star topology. So suppose what is the meaning of this star topology? So in the star network, what happens is suppose this VSAT wants to communicate with this another VSAT, which is nearby it. It cannot directly talk with this VSAT here. First, this fellow has to send its signals to this hub, and then hub will send the signals to the second VSAT, to the destination VSAT. So here hub is acting as a central node, which takes care of the communications between different VSAT terminals. Okay, so otherwise you can have a mesh network. So in the mesh network, what happens is any VSAT can talk with any other VSAT terminal. So suppose if this one wants to talk with this one, so then directly it can send the signal through the satellite to that particular VSAT. There is no need of any hub in between. But again, it defies the own concept of the VSAT network because why we have come to this VSAT is we wanted this hub to be a powerful thing, the transmitter side to be a powerful thing, more headache and more burden towards the transmitter, so that these receiving devices can be low performance, low cost, flexible, and no need of having large gain or large aperture because we are sending a lot of power from this powerful central control hub. So that's why star network is preferred. Like it's also called as a double hop link because as the name itself suggests, so one time you have to this VSAT one has to send its data through the satellite to master hub or master control hub, and that hub will again send it to the VSAT. So that's why it is called as double hub. And this makes sense because VSAT were originally made for making low cost and small devices at the receiving end. So they just send their data to the hub and hub will take care. So in contrast to this, if you have a mesh network, it is single hop where VSATs can talk with the other VSATs. So directly communicate with any of the other VSATs without a need for a central hub. So this is called as mesh network. But again, these VSATs have to be powerful enough to send that much power, and they should have all that signal processing abilities. And so it makes it complicated. And how does this satellite perceive for a star network? So from the viewpoint of a satellite, it's just talking to a hub on this side, and this side it's broadcasting the information to different VSATs. So this side it is just broadcasting. It does not worry which information is intended for which VSAT terminal. The VSAT terminal itself will have that much knowledge to identify whether that message is related to it or relevant to it or not. So satellite does not bother to send it to particularly VSAT 1 or VSAT 2. It is the responsibility of these VSATs to collect their relevant information, and they have that much logic also. This side it's only hub, nothing else. Okay. Compared to this, if you see the mesh network from the satellite's perspective, it has to get the information from one end and rebroadcast it to all the. So actually, these VSATs are again this side only. These only. These are not any other VSATs. So this also you put this side only. Okay, so it's like from these VSATs, it's coming to the satellite. Again, the satellite is sending back to broadcasting to this overall range. So whichever VSAT is the destination, it will decode the signals. Okay, so that is the two-way implementation. Okay, so then one particular thing of concern is that when we use these data services with the satellite, with the VSAT networks, the problem is that the terrestrial, this IP or internet protocol was designed to act as a terrestrial protocol. So accordingly, the delays were designed to match that terrestrial propagation delays. So that will not be useful here. And VSAT is a device which has up to three layers of intelligence. So it can understand physical layer, data link layer, and network layer. So accordingly, what we have to do is, so what is the problem with the terrestrial network of internet protocol? So the problem is once the transmitter sends a message to the receiver, it waits for 60 milliseconds to get back the reply from the receiver. Like there are two methods. One is ACK plus NECK, negative acknowledgement. So in one protocol, it's like once the receiver receives some message, it has to send back the acknowledgement, either positive or negative. If it has received all the packets correctly, it has to send a positive acknowledgement. If it has got some errors, it has to send the negative acknowledgement. So then one more method is to is used in the practical internet protocol. That is, the receiver keeps quiet if there is no error in the received packet. Only if there is error, it will send a negative acknowledgement to the transmitter, and it will ask for the retransmission. So it tells that transmitter to resend that particular frame or packet which is erroneous. And for this, receiving this reply, the transmitter waits for 60 milliseconds. So within 60 milliseconds, if it does not get any reply, then it thinks that the connection with this receiver is lost and there is some trouble with this receiver. Now, the problem with the geostationary satellites is that the round trip delay itself is 260 milliseconds. So with this kind of delay, this is only for the round trip delay, but you have signal processing delay and all that. So for that additional time is required. But within the 60 milliseconds, if you use the same logic for this geostationary satellite, every time the transmitter thinks that receiver is disconnected, every time transmitter thinks that the receiver is not ready or lost or something. So to avoid that, we need a bridge between these two networks. This is the terrestrial network. This is also terrestrial network. In between this VSAT network is there. So we have to act as a bridge between that. And in between these layers, there are some protocol modifications in order to uh, provide this larger timeout window. So instead of 60 milliseconds, maybe we can make it as 300 milliseconds or something, so that it matches to the requirement of the propagation delays in the geostationary link. And so this we may keep it as transparent to the terrestrial network. And so this method is called as spoofing. So enables the packets to be received properly. So all these things are that only. And one particular modification which we generally make is to change the protocol from modulo 8, like HDLC is a link layer protocol, which is in the data link layer. So it generally provides modulo 8 operation. So what is modulo 8 operation means? It will send only seven unacknowledgements, unacknowledged frames before stopping. So seven frames are sent to the receiver, and after seven frames also, if there is no reply from the receiver, like negative acknowledgement or positive acknowledgement, it will stop the transmission. It thinks that the receiver is not in position to receive, or there is some fault in the link, or the receiver is not ready. So but this is very much less for the geostationary satellite link. So one modification is that instead of modulo 8, we can go for the modulo 128 operation. Thereby we are increasing the that window size. If you know the sliding window protocol in network, computer networks, so if you go for a higher size of the window, then more buffer time will be there. Like you can store more of the packets or frames in that buffer before deleting them. So if you go for 128, then 127 frames can be sent without waiting for an acknowledgement. So that is lot of time. So definitely that propagation delay will be overcome. Like 127 frames, and till 127 frames you are not expecting any uh, reply from the receiver, and this time is more than sufficient to accommodate the delays. And accordingly at the receiver, we should have the proper buffers in order to reorder the packets or frames. So buffers are needed at receiver to reorder the packet. So sir, why we have to reorder means, suppose fourth packet or fourth frame is having some error, but fifth, sixth, seventh packets have come, because this is not waiting for the negative acknowledgement. Fifth, sixth, up to 100 packets you have got, they are all perfect, only the fourth one is having some error. So you have requested for a what is that, retransmission from the transmitter. So by the time it will come, you should be able to buffer this 5 to 100 packets, because you cannot uh, decode without that fourth packet, right? You understand? So fifth to 100 packets, you should have some facility to store it. Now once the fourth packet is retransmitted, and when you get the correct version of that, you put all these things in line, and then you send it to the demodulation or decoding logic. Okay, so that is how we do it. So then there are other things like in VSAT only, VSAT Earth Station Engineering, what kind of antennas you have to use, and simply we are talking that data has to be sent between the hub to the terminals, like how it has to be sent, whether you have to use TDMA or FDMA or what kind of modulation you have to use. Then earth station engineering is how the antennas are designed and how is the link budget calculated for this. So Vsat links, how is the link budget calculated? Like again, you have to consider how much is the size of the Vsat antenna, how much gain, what is the characteristics of the central hub, how much antenna size is there, how much power can it radiate, and all that we have to do for the link design. So generally, we don't discuss all those things. Okay, so only till this two-way implementation and delay consideration. So delay considerations is important in the VSAT. So what we are doing is we are making some temporary arrangement which is not known to the terrestrial network. So we try to modify the protocol that is called as protocol emulation or spoofing. So this happens only inside the VSAT. The terrestrial network is blind to all these changes, so it does not bother it about all these things. Okay, so these details are there, like all these details. When you implement it, you will understand all those problems. Okay, this one. Okay. So that was module 6. So quickly I will give an overview of module 7. So what are we up to actually in this? So once we finish this, the main concepts will be over. Then after the 2nd June, we can discuss like revision or something like that. Or what is the pattern for the pattern anyway, you know, what are the important questions and all that we can discuss later. So now I will give a quick overview of the module 7. So as I already said, now if you are in a different mood, then also no problem, you save the recording and you can play it later and understand. So here one topic is the DBS TV and second topic is GPS in the module 7. These two are the main topics. So before the DBS TV, first of all, it comes under the category of direct to home television. So there is a broadcast center and geostationary satellite in between. Then it is broadcasted to all the users. So user will have the rooftop antenna and receive the signals directly. So that is the main concept of direct to home. Nowadays they are talking about direct to car also. The top of the car they want to put this antenna and receive all the channels inside the car. Okay. So, but there you have to take care about the mobility of the car and the Doppler effect also. And always you may not get a line of sight consideration, because if it is on the top of your home, you can guarantee that always it is line of sight with the satellite. There is a clear path between the satellite to your antenna, but in the car, it's not possible. Okay. So within the DTH, two services are there. TVRO is the television receive only service, which is more complicated than the DTH, and it has more capacity, more number of channels, and high power, like large antenna compared to the DTH. So then one problem is that it is full crystal clear. TV receive only is crystal clear, and no compression is used in that for video. So therefore, uh, each transponder can take only one channel, and 16 transponders can support only 16 TV channels. So if you want a wide variety of channels, you need to be in communication with several geostationary satellites. So therefore, the antenna on that should be steerable. Okay, so steerable is like steerable dish. You can tilt the position of that dish in order to talk with another satellite. If you want to receive some other channels, you have to position it to that particular thing. So we won't uh,
position it, there will all will be digitally operated. If you select a particular channel, then it will go to the microprocessor and it will take care of moving the overhead antenna in the appropriate direction. So this was in the C band, large dishes and difficult to operate, complicated and costly. Therefore, the second option was this DBS, Direct Broadcasting Satellite Services, where you have this DBS satellite satellite downlink, which is a wireless medium. So receiving dish is there through the coaxial cable. It comes till the TV set, which has the set-top box, and inside the set-top box, what is happening? Like at the receiving dish, after the receiving dish, there is a low noise block or low noise amplifier. After that, it comes to the demodulation block. Inside the set-top box, all these digital signal processing techniques are done, where you descramble it and convert it into the analog form. And once you select a particular channel in your remote, only the particular scenery or the visuals of that channel will be extracted and displayed on the TV screen. Okay, so all this is given here. So then this is how the transmitting station looks like, very big antennas. So this one uplink at the station, followed by so many home DBS receivers. So this is direct broadcast or DBS TV. So because it is Q band, the frequencies are high and therefore the end terminal can be of a lower size because of the lower wavelengths. So overall, how does this look like? Video, audio, data. So all these are baseband multiplex. For video, we use MPEG decoding or MPEG compression. Then there is some forward error correction. We add some redundant data in order to protect the bits. So if you have 10 bits, generally we go for additional bits, 4 or 5 additional bits or 3 or 2 additional bits in order to enable error correction at the receiver. Then proper modulation is chosen. After the intermediate frequency block, these are up converted to a exact carrier frequency, and you have the low, what is this? High power amplifier and low power amplifier. Then it is sent to the gateway uplink earth station. So uplink frequency, as always, is more than the downlink frequency. The satellite has a mixer in it and it will convert this into 12 gigahertz. Then we have a home satellite receiving dish. Out of that dish, we have a low noise block, which is having a low noise amplifier. After that, it will low noise block is like it will try to reduce the noise and only filter the required signals, then followed by the appropriate demodulation and FEC decoding. So whatever error correction mechanisms you have put at the transmitter, here we have to remove all those and get only the exact raw bits. After getting the raw bits, you have to perform this baseband demultiplexing and separate out the video, audio, and data to the TV set. Okay. So this is the overall block diagram, and particular block diagram of a DBS TV receiver is you have to draw this one. So the questions can be like describe the operation of a DBS TV receiver with a neat block diagram. So you are supposed to draw this block diagram and explain what is happening in this. So it is a continuation of the previous thing, like the DBS signal is received in this many gigahertz. So it will be sent to a RF block. So here low noise amplifier, then image frequency rejection. So this is first level of mixing or first level of down conversion. So there are two stages of down conversion. So basic model is this one. Like low noise, this is a very simplified diagram. Low noise amplifier then goes to the set-top box. Here uh, IF stage and demodulation. So here it's more zoomed version. Low noise amplifier mixer. First it comes to this range 900 to 1400 megahertz in the first IF amplifier. So then this is all the low noise block. This fully is the outside the your home. So low noise block is at the rooftop along with the antenna. So low noise block converter mounted on the antenna feed. Okay. So after that coaxial cable to set top receiver. So this set top box is this coaxial cable, which is here, this fellow. So the black wire which you have from the dish TV to your set-top box, that one. Followed by here one more frequency conversion stage is there. So again the band pass filter mixer IF amplifier. So here it's coming to 70 megahertz. So if you see from 12 gigahertz, it has come to 70 megahertz. Then followed by the demodulation, and here if you see, according to the channel which you want to see, this microprocessor will give the instructions to the frequency synthesizer, and it will have a tuned local oscillator which will be uh, selecting only that frequency. Like, number of channels are there, so each channel will have its own frequency of operation or the bandwidth. So here using this microprocessor and frequency synthesizer, this tuned local oscillator tunes to the particular channel which you are seeing or which you want to see, and after that only those particular programs will be sent for further. Okay, so till here only all the 500 channels will be there, like before the mixer stage. And once you tune it to the required thing, only the particular channel will come out. And then this one is inside the set top box, like all this decoding, baseband multiplexing, forward error correction decoding. So this one, descrambler. So inside the set-top box, all the signal processing is done. Inner decoder, de-interleaver, outer decoder, digital demux, MPEG 2. Nowadays they are using MPEG 4 for the Tata Sky, etc. Airtel Dish TV. Then D to A conversion, video and audio are sent to the analog output. So at the TV, even though if you have a smart TV or anything, HD TV, finally you have to convert it into analog, and also you have to take care of the sync between the video and audio. It should not be like a pirated movie where video is something happening and audio is lagging by 1 minute or 2 minutes. So both should be in proper sync, so you have to overlap those waveforms. Okay, so this is the detailed block diagram of the DBS TV receiver. And what kind of error correction or error detection mechanisms are used? So describe the error control. So one thing you have to understand is, in the term end or in the FAT exam, if it is like a 2 marks question, you need to draw only two marks worth, or you need to write only 2 3 lines. Don't waste. Suppose if it's 2 marks, there it will be mentioned there. It's asked for 2 marks, so you just write according to that marks. Don't if I ask 2 marks, don't write this much paragraph, because you will waste your time. So if we ask separately, like describe the error control mechanism in the DBS TV receiver, just you draw this thing, and as we can see, many digital methods are used for error correction in the DBS TV. That's all, one line answer. So what here at the input side, at the uplink earth station, they use Reed Solomon encoder. Then interleaving is like uh, interleaving is something like scrambling. Like suppose if your message is ABC, so here we may add some redundancy bits. Then interleaving is like you just scramble the positions. Then convolutional encoder, you add additional bits. There is a particular procedure for so 3 by 4 rate convolutional encoder means for each 3 bits you are making it as 4 bits. Okay, so you are adding additional redundancy bits. So instead of ABC, maybe you are making ABCA, and instead of CAB, you are making CABC. So this is the redundancy you are adding, and the same opposite process you have to do at the receiver. So I think all these things you should have studied in the subject ITC, but still all the details we don't want here. Just to draw this and tell that this is how it is done. Then similarly we will have a link budget for the DBS TV. So no problems, no numericals in the module 6 and module 7, only theory is there. So this is only for your understanding. So even for the DBS TV, we should have a link budget. We should calculate the transmitter power, what is the bandwidth, noise bandwidth, signal bandwidth, everything we have to calculate, and finally see how much whether the C by N is above the required thing. So generally in the last class, C by N, minimum C by N should be 14 dB. Here it is 16 dB, and is telling throughout the US, it's better than 99.7 availability at this much parameters. So maybe we can see our Indian scenario and see. Okay, so what is this? This is the uplink earth station. So in the uplink earth station, what is happening? So if one batch has got downlink, obviously the other batch will get uplink, because we have two or three batches, three sets have to be made for the FAT exam. So describe the block diagram of a DBS TV transmitter or uplink earth station. So first you take the analog audio and video signals and pass them through the ADC. Once you get the bits, you perform the MPEG decoding, MPEG compression for the video part, and then multiplex. So other digital signals are also multiplexed here, and then coding you are doing. So this entire block you can just replace with error control coding. Error control coding. After that error control coding, you are modulating it to a carrier 70 megahertz, then IF amplifier up converter. This time you are using a mixer to increase the frequency, followed by low power amplifier, high power amplifier, then multiplexer of other RF signals. Okay, these are other channels, actually other channels. Here it is small data related to that channel. Here they are other channels, and then send it through the uplink antenna. Okay, so this is the overview of the DBS TV. Then we have GPS. So GPS, you know what is GPS? Global Positioning System. So I will tell you the main logic of this. So again, because of the pandemic, I am hurrying up, because there is a wide gap of many days from today to up to 1st June. So you may forget that, and after that we can't predict what will be the position. So that's why I'm giving you a full overview. The slides will be uploaded and you can study. So even without my help, if you want, you can go for the FAT exam. So that is the main aim with which I am teaching today. So mainly what is happening in the GPS position, I will tell you a simple example. See, suppose if you want to know where are you right now. So if I tell that you are 220 kilometers from Bangalore. So you are 220 kilometers from Bangalore means this is Bangalore. So 220 kilometers means you can be here, you can be here, you can be here. You can be anywhere on that circle of radius 220 kilometers, right? Now, one more thing is I can tell you that you are 140 kilometers from Chennai approximately. So suppose if you are 140 kilometers approximately from Chennai, so these are not to scale. So Chennai 140 kilometers means you can be here or you can be anywhere. You can be in the Bay of Bengal also. But let us say I have these both information, that I am 220 kilometers from Bombay, Bangalore, and 140 kilometers from Chennai. So now I know that I am somewhere on this place. Then I will get one more measurement. So generally these two are circle. These are on the land. So these are circles. Now one more reading I will get maybe from Tirupati. I will tell. So I'm 100 kilometers from Tirupati. Okay. So if I'm 100 kilometers from Tirupati, then I can exactly get a particular point on the surface of the earth. So this is only 2D. Now imagine 3D. So in the satellite, everything works in the 3D. So imagine a sphere. You are this much distance from a given satellite. Satellite 1, you are at this much distance. So imagine a sphere, and then again one more sphere, and then again one more sphere. So at the intersection of those three spheres, there will be some area. You are there. Okay. So to understand, we go for this 2D thing, circular thing, but reality is 3D. So you are that much away from the satellite means in a three-dimensional big spherical ball, you assume at the middle of that spherical object, that satellite is there. So you are that much far away from that satellite means in the three dimensions you are somewhere on that ball. Okay, so like that, this method is called as trilateration. So trilateration. So using that, we can find out the position of the different receivers. So basically, minimum three satellites, and GPS constellation has totally 24 satellites in the lower Earth orbit. GPS constellation. Okay, so out of that, at least three are required, and fourth one is used to get the precise timing information. So overall, four satellites. If you can get the data from four satellites, that is sufficient for your operation. So then, how does it operate? Is like so basically, you find out how much far away you are from each satellite. So there is totally 37 or many satellites are there. So you have to latch to one of them one by one and get the information like how much time you are taking to receive that signal from the satellite. Based on that, you get R1. Similarly, with the second satellite, you get its signal, decode it. You will understand how much far you are from that satellite. Then R3, like that you do for all the satellites. And here there are two codes. So what are the GPS codes? So GPS codes are two. One is the C by A code called as course acquisition. So here you get a overall idea of how far you are from that particular satellite. Then second one is precise information. So once you decode the C by A message, you can go for decoding the precise information. And by doing all these things, you will know how far you are from that particular satellite. Okay, so how this information is organized is all these satellites use spectrum, so CDMA. When the receiver wants to latch to a particular satellite, it wants to lock to a particular satellite, it will use the pseudo PN sequence of that satellite for reception of the particular satellite. And since it is CDMA, all the satellites send their information at same time and same frequency of the particular sat. So if you know, once the GPS receiver is on, it will search for the different satellites. Overall, 37 uh, satellites information can be obtained, and then based on that it will log to one by one and it will get this information. So what are the major sources of errors in the C by A code? So basically it is all timing. Based on the timing you are calculating how much far you are. So the clock error should not be there, clock errors and ephemeris errors. And the other types of delay are because of the ionosphere and troposphere or in the receiver noise, or there is multipath communication, like instead of a direct line of sight, if the signal bounces from somewhere, then it may cause additional delay and you may have an error in finding out the proper time. So then question is like draw a simplified GPS receiver block diagram. So any receiver has receiving antenna, low noise amplifier, mixer stage coming to the IF stage. Inside the IF stage, you convert it into the digital and perform the digital signal processing. And then you have the microprocessor which is analyzing all this information, and finally you get the, so they have timing data, clocks, every navigation message. So describe the format for a navigation message of a GPS. So there is a particular format, preamble and subframe, all that. Then finally you display that one. Okay, so since only one question is there, you can easily study this one, the simplified GPS receiver. Then what is differential GPS? So in differential GPS, we are not worried about the exact XYZ coordinates of no need of exact coordinates. In turn, what we want is we want how is this receiver oriented with respect to a fixed station on a ground. So fixed location on a ground. So so general GPS is like we want to know the XYZ position of the receiver. But in differential GPS, we are least bothered about our position in the space. We are bothered about how we are oriented to a fixed location, like a airport or like a what is that? Seaport. Okay. So when you want to land the aircraft or when you want to take the ship into the particular berth in the seaport. So there it becomes more important to know how you are oriented in space with respect to this one. So there you, it's of least concern whether with respect to satellite you are at which position. So in that we use the differential GPS. What we do is we get our location with respect to the location of this fixed point on the earth, that is the airport or something, and our main aim will be only to reach that receiver or to make that error between our position and that position as zero. Okay, so that should be the main aim, and that is the application of the differential GPS, where we are least bothered about our position in the space, but we are most bothered or most concerned about our position with respect to a fixed body, so that we are reaching to that. So even there is error in the XYZ, you don't worry about that. Main thing is only with respect to that location, you orient yourself properly. Okay, so I think this is the overview which I wanted to give you. So just I will play these slides within 1 minute. So DBS TV, what is there? So all these slides are not useful. I will give you the slides. Then for GPS also, why GPS was implemented? It was for the defense applications, for the military applications. All this we don't want. This is only theory. No need to read all that. So how the position is calculated and how, so timing is very important in the GPS. How do you demodulate all these things? So here also the main blocks are not written, only the errors are given. So basically, so I will provide you the proper PPTs that you can study. Yeah, so these were the things which I wanted to highlight in today's class. I will stop the recording.